Okay, guys, this is the FORTH 2020 meeting of February, and I have the great pleasure to present you Andreas Spiess from Switzerland. He's a YouTuber, a very famous YouTuber of embedded systems. And I pass you the microphone, Andreas, and say hello from Brazil. I am in Brazil.
From sunny Brazil, I hope. Here is winter in Switzerland. So hello again to everybody. Maybe some of you know me, at least from my videos. We obviously have similar ages, at least if I look at the faces here. We are no more 20 at least. That is probably a common thing. My background is in engineering. But I left engineering in a different way. I did an MBA and a PhD in business administration, and then worked my life to feed my family in the enterprise resource planning software field. So I was not an engineer as a profession. I just worked about 5 years as an engineer in R&D. And then when I became older and the family phase was done, I came back to the Arduino stuff and all these kind of things. I was also quite an active ham radio operator when I was young. I worked for the Red Cross in some not so nice places in Africa, in the Middle East, or as we called it, Middle East, where it was always a little bit shooting and stuff like that. So, and there they needed people like me who were able to do the wars and who also to build a radio station, to maintain a radio station and so on. So that's what I did in my youth. And I came back to this hobby basically a few years ago, and then I was a consultant, or I'm still a consultant for this enterprise resource planning. And then people started in 2014 or so. People started, or my customers started to talk about their social media. Shall we do something? What shall we do? And so on. And I'm not a guy who tells things he does not understand. So I said, I have to learn it somehow, that I, at least if I'm asked, I have an answer. And I'm a guy who has to do something to learn. I cannot learn from books or from I have to have a project to learn. And then at this time, I had 3 choices: Facebook, Twitter, and YouTube. They were considered to be the social networks back then. And for me, Twitter, I still do not understand how this really works with the threads and so on. Facebook was not my world. It was the world of my wife probably, or somebody else. This was not my world, but YouTube was my world because I learned already a lot before on YouTube. And on YouTube, you find everything. The first search today is no more Google for me. It's always YouTube. Because just my car, I have an old Volvo, and because we do not use it very often, we do not service it every year, but every 2 years. But this bloody car wants to be serviced every year. And he is nagging a whole year long. Please service me the whole time. And on YouTube, for example, you find a video how to get rid of this nagging thing. It's not easy. You have to know exactly how it's done, but YouTube knows. And every 2 years, I have to search for the Volvo and for this video, and it's still there, and I can remove this nagging. And if YouTube knows that, it knows pretty much everything else too. And for me, videos is something also for programming and so on is much better than writing. And why is that? Because in writing, the focus of the writer is always basically, he is an expert and he writes what he thinks is important. But for me as a beginner, maybe completely different things are important for that moment. And if he writes it down, he omits all the rest, and I never get this information. With a YouTube video or with a video in general, I might see the screen and I see, oh shit, my screen is completely different than his. He doesn't tell me anything about that, but I just see it, or I can see something above. He never mentions it, but it's on screen, and I get a lot of additional information. Or try to explain somebody how to ride a bicycle. It's just hard to explain, but if you can show it, it's much easier. And this is why I think video is really another quality for explaining stuff. And this is why I choose then YouTube. And I said, okay, I have a budget of $1,000, and I want to create a channel with 1,000 subscribers. That was my plan, was my project to learn. Basically, it was a learning project, was an investment of $1,000 to learn this social stuff. And then after I started in summer, and in November or so, I had to think about how to spend this money wisely and so on. I learned quite a few things, but in November or so, or December, I had my 1,000 subscribers. So the project was done. Unfortunately, I was addicted by then. And why was I addicted? It's quite simple. I always create a video on Sunday morning. I publish it at 9 o'clock my time. And at 12 o'clock my time, I get more compliments than in my whole professional career before. So, and these compliments, they are not because somebody has to say something. It's completely up to them. You can watch the video. You do not need to write anything, or you can write something not so nice, whatever. But the guys who say thank you, I learned something, or sometimes tell me their whole life story or whatever, they do it just because they want. And this was for me a very important thing. Plus, the second thing is I was able now to create a community around my hobby, basically, because the guys who watch my videos are very similar. I read very often. You can read my mind, for example. How do you present something? I need it for next week, or I need it last week. So, and this is clearly because we have a community, and I think it's very similar to your community, with very narrow focus in a way, and all are similar. So I continued up till today. It was always my hobby. It was never my profession. So I did not need to make money and I did not have to do decisions. For example, younger YouTubers, if they want to live off it and feed a family, then they have to do decisions I do not want. For example, do a lot of advertisement, do product testing, stuff like that. I don't do that. I do not make any paid promotion other than the videos from YouTube. That is all. I also do not do mid-roll ads, which separate my videos. I do not want this money from YouTube or from whom else, because I do not like this kind of advertisement. So I do not allow YouTube to interrupt my videos. So these are things I can do because it's my hobby, basically. So that's what I do. My love is wireless. It's sensors, it's microcontrollers, but it's usually not very deep. I said it yesterday to Peter. I'm always standing on shoulders of titans, because I need projects, I need things which is prepared, but I can do a lot of good things for the inventors. Let's say, for example, if somebody had a platform created, a Polish guy had a platform to track weather balloons worldwide. And I thought this is a cool project. I still think it's a cool project to hunt weather balloons. Every day they launch about 1,500 weather balloons around the globe, and if you know how you can catch them, it's like a little bit it's fun for me, at least, if you find one. So I showed this project on my channel, and on Sunday his infrastructure was crashed, and on Monday morning I apologized for that, and then he came back and said, yes, I have now 30% more traffic on my platform, and since then there are even much more people doing this. Another example is there was a satellite launch from a 16-year-old Spanish guy, and I thought this is an important thing also for young people to encourage them to do Mint or just electronics and stuff like that. And I featured this project. Unfortunately, the satellite did not work. It did not extend the antenna nor the solar power, the solar panels, but still we all watched the start and so on. And we created then also a global network to receive the data from such satellites. And this satellite ground station network now has 650 ground stations around the globe. It's much bigger than NASA or SpaceX together. Of course, it's a little bit smaller in capabilities, but still we can now track all these CubeSats from different universities and so on. We can track around the globe, and it's a network. So I didn't create the network, but I made it possible that many more people knew about it and were able to participate.
Andreas, and one question about ESP32. Why did you choose this platform?
Because of wireless. I mean, everything is connected these days. I do not have one project which is not connected. You get such a lot of opportunities if your device is connected. And there are several possibilities to connect, but the Wi-Fi is the cheapest and it's ubiquitous. I think this is the word. So everybody has it. So and this was the first time that we had a chip for $5 or something which were capable to do Wi-Fi. And now with LoRa, that is another possibility. There you can use an STM or an old Arduino or whatever. You do not need an ESP32. But for the rest, I usually end up with an ESP32 because why not? It's okay. It's fast. It has dual cores if you want. It has plenty of peripherals. It more or less it has RAM more than all others together. Also flash is abundant, so it's a class of its own, in my opinion. And you get also the different modules. We have this here. For example, this one is for ham radio. It's on a 70 centimeters, an APRS tracker. This one is on 868 for TTN, a tracker, completely different network. And this one is to hunt the balloons. And inside, it's always the same, more or less the same thing. And we can buy these boards, including LoRa module, including ESP32, including battery management, including display, everything included for less than $25. And I mean, I get now satellite messages from 2,000 kilometers away with an antenna like that. This is the antenna. A simple ground plane this long, and I get a satellite. I can receive satellites 2,000 kilometers away with a chip which costs $5 or $7. It's mind-boggling for me. I mean, when I was young, everything was expensive, and today it's everything is cheap. We get. I just create a video, and these are vector network analyzers. They costed $50,000 when I was young. Now you get it for less than $100, and they work. They are completely okay for what we need. We get really, the only thing we do not get is ideas. The ideas is the most scarce product for the moment in my world. I see a lot of people without ideas, also young people sometimes. And this is, in my opinion, where we lack of, and the other thing, of course, is time and the ideas. These are the two constraints in a way of our time. That it's no more money, really not. I mean, I have viewers who write me, they have to save till they can buy a soldering iron for $10. That happens, but this is not the norm. In the Western hemisphere, people have enough money to at least do a few of these projects. And this is also why on my channel, $50 is a range where I stop usually. I do not present things which are, in general, which are much more than $50. I do not.
We have a question from Jad. Hello, Jad.
Hi, sir. How are you doing?
Hi.
Jad. Yes. How are you, sir? We are really fan of you. We was watching your videos during the 2 years. We started. We are how to say? We are electrical engineers. We have more than 15 years, and we started working with IoT solutions. We started our business, how to say, we started the first solution we made. We made a smart sensor for doors, etc. We use your recommendation regarding using specific type of regulators and also batteries. Everything is going smoothly. We're starting, how to say, we're starting building our PCBs, and we're starting also printing, how to say, the enclosure design. Everything is going smoothly, actually, but the problem is that when we tried to build our enclosure or to try to print it, it was pretty expensive. So if we think about how to produce a quantity of that enclosure, it will cost us a lot of money if we try to sell it or something like that. So do you have any recommendation if we decided to go in this direction and start producing a product which could be consumable by people, especially if we are looking for a special enclosure? What is the cheapest way and the easy way to make it? This is question number one. Question number two, we're starting also with the, how to say, hydroponic project, pilot project. And we have lack of sensors, especially a specific type of sensor which detect the oxygen, which is, how to say, the percentage of oxygen inside water and etc. Do you have any recommendation regarding these kind of, how to say, hydroponic or aquaponic projects? If we are looking of the specific sensors, how we can find it, and if not, what to do? Thank you, sir.
One thing I always can say, I never know more than Google. I never know more than Google, because if I have a question, I always use Google. And as I said before, if I have something project oriented or so, I use YouTube. But for sensors and all these kind of things, use Google. And I often use image search also, not only text search, because with image search, our brains is very good in image search in a way. And there you can browse things much faster. And if you have something in mind already, then image search is a very powerful thing. But it's usually when I talk to other people, people say Google is a search engine. For me, Google is not a search engine. Google is a find engine, because searching, everybody can search. Not everybody can find. And this is something we have to train. And I cannot tell you how I do it. I really cannot tell you. It's like driving a bicycle. I never can really tell you how I do it. I just can it. I'm capable to do it. But you have to exactly understand which keywords, and then you will find, because you said something special. But if you cannot name this specialty, Google will not help you, but also you are lost. The first thing is your specification. What exactly you need for, if it's only CO2 sensor, you will find more or less 2 or 3 types. One is the lambda sonde in the cars. The other one is the one we use for this COVID stuff I made a video about. And then I think there is one which does it in the air. But I'm not a specialist there. But if you need something very special, I would always go for Google. Now, for casing, I never do production runs. I sold hardware in the 80s. This was still fun. The cheapest computer from Digital Equipment Corporation, where I worked, was 1 million. Even a Microvax was easily $1 million. This was fun, and we were able to entertain the customers and all these kind of things. And today, a computer costs a few dollars, and it's no business. And hardware is a Chinese business. It's no more a business for me. So I do not do anything with hardware. So I cannot recommend something. As I showed before, I do everything 3D printed. I completely stopped. I had a milling machine. I completely stopped with metal. I do all 3D printing. And from what I understood now is JLC PCB, for example, started a manufacturing operation where
PCB gateway.
Sorry?
PCB Gate, I think. There's too many manufacturers. We contact with them, and they provided a good quality PCB, actually.
No, I do not talk about PCB. I talk about casing. They started now to offer also cases. They offer metal printing. They offer metal milling and all these things.
What's the name of the factory? What is the name of the factory or the people?
JLC PCB.
Can you please type it so I could? PCB.
Watch any electronics video except mine, and they will be there as a sponsor. Yeah, somebody wrote it.
JLC PCB. Okay.
And look at them. I never tried it, but they started to offer these services.
What about the quality of the 3D printing?
Sorry, I need to interrupt you, Jad. But we are in a language programming group, which is FORTH, and our main objective today is to talk with Andreas about compilers, ESP32, and showing him what the group does. So I have a question for Andreas. We've been talking, Andreas, about your impressions with interpreters and compilers. Probably you have something to tell the guys here in the group.
I did my most successful video on YouTube was a video about MicroPython, more or less, and it's the one I do not like at all, in a way, because it's the only video I decided not to answer any comments. all other comments on my channel, and it takes me hours and hours, I answer all comments on my channel, except the video about MicroPython. And it has a reason. This was extremely controversial, and a lot of opinions which were not nice and so on, not against me, but mainly against interpreters and stuff like that, against new things. But bottom line is, people do not want to move away from C++. That is the bottom line. You have a few beginners, let's say, they like this MicroPython, but the guys who do the heavy lifting today in the industry, they do not move away from C++ for the moment. It's just they have a lot of reasons. I didn't want to answer the reasons because they usually are very personal and probably even not right in current. My point was, I started with programming assembler. I did not particularly like it, but it was the only way to program microcontrollers back then in the 70s and 80s. And then came C, or other PLM and other higher level languages. And I never looked back. I never looked back to assembler, because it gave me such a lot of freedom and productivity that I never wanted to look back to this day. And this was possible because we were able to invest a few cycles from a microprocessor to save engineering hours. Because microprocessors became cheaper and more powerful, engineering hours became more expensive. This is why C and C++, so whatever these high-level languages emerged and replaced more or less machine code in many applications. Now, my theory was in this video: are we now at the same level again? If I compare an ESP32 with an Arduino, it's way faster, and most of my ESP32 sleep or delay. I just have to slow them down because they are too fast for most of the things. And my question was, do we again replace machine cycles and engineering hours? That was my question basically in this video. And Python for me is a good language because it's good with strings. I hate strings in C++. I never learned it to work proper with them, and it's always a nightmare. I always lose 50% of my debugging with strings or other variable mismatches and stuff like that. I'm not a programmer by education. I'm more an engineer, but Python was much better in this respect. And but this was my question. It was as a question. It was not as mentioned as a statement. Most people took it as a statement and opposed. And the same question will come up tomorrow in a video where I will talk about Toit. Toit is a new environment, I would call it, with a new language. And it's made from a few Google drop-offs and Uber drop-offs. Younger people, middle-aged, 40 years old or so. The one was one of the main developers of Google Chrome. So they come from a completely different environment. They do not come from microcontrollers. They come from the bigger computers. And they ask themselves, how can we implement this? And if you are interested, you can have a look tomorrow. They have now a containerized system which can be remotely deployed and so on, but it's also an interpreter. It's interesting. And the language is like Python. It's a new language, but the syntax, it has no curly braces. It is very similar to Python. Now, this was also the intention, because Python these days is the most learned language, except from lower level languages. So they thought that they will find a lot of people. But I compared then this new environment with Arduino and with MicroPython. And the technology is okay, but they have no community, they have no examples, they have no libraries. And this
I have a proposition for you. We want to make you aware of the FORTH language, which was invented 50 years ago, or more than 50 years ago, by Chuck Moore in USA. And we have this new implementation for the ESP32 made by Brad Nelson in California. And we want to show you a little bit of what we can do with this ESP32forth, which is a language which, in my opinion, is much interesting than Python, because we have no syntax. There is no syntax in FORTH.
But what where you stopped me was, I do not care too much about the language, as long as it's good in strings, because string is my main thing today. I mean, if then else is everywhere the same, but I have a lot of string handling in my projects, because user interface and all these kind of things. As long as the language is good with strings, I do not care about the language itself. But what I care about is examples and libraries. The ecosystem around it is the most important thing, because, as I said, I have to stand on shoulders, and most of my viewers need these shoulders too, because they have no time. As we said before, they have no time, and
I can answer this question. It's very valid. It's a valid question, Andreas, and it's the same opinion that many people have. We need libraries. And what attracted me to ESP32forth? This is a forth written in C. In C on the, you can use the Arduino IDE, for example, or any other environment that you like more. You simply download the source and it will compile as a binary. After that, you install into the ESP32 chip, or in many versions, also on the ESP32 CAM. And the interesting part is that if you need some sensors, or you need a library for anything else, you can add it, because it's written in C. This is the great advantage.
I just wanted to, you asked me what is important from my point of view. It's no more the language these days. It's much more about the examples, how many people know it, and all these kind of things. The community. And why is Arduino so successful? Because it's the best programming language, because it's the best IDE, because it's the best 8-bit processor, whatever. No, not at all.
Because of the people. Because of the people, yes.
Because of the environment. And I think this is the most important thing for somebody who works with languages. It's no more about languages, at least not for me. For sure, if you do rocket science or whatever, where you go to the very top of technology and so on, there for sure the language matters. For sure the language matters, but not on a level I work, where I do IoT projects in a way, or just assembling different sensors, microcontrollers, connect them with the infrastructure. These are mainly what I show on my channel. So the language itself is for most of, and as we saw, people do not want to go away from their language they invested. I mean, a few of you said, we do this for 40 years. You are the same kind. You do not want to leave FORTH, in a way. And
well, in real, most of our programmers, work professionally with C, with C++, with Java, with anything that they JavaScript, with everything that it's normally used professionally. And FORTH has become a hobby for many of us.
Yeah, but you still love your language in a way, and this is good. This is very good. But I think it has a lot to do with not with hard arguments. It has to do with where we come from and stuff like that. But anyway, that was you asked me for an introduction, and I stop now.
It's about faith.
Sorry?
It's about faith, belief.
Yeah, in many cases, I think probably a few people do a formal judgment and all these kind of things. But for example, the enterprise resource planning I worked for was SAP, and they have a completely proprietary language. It's called ABAP. But it has a huge community around this ERP stuff. You can get a lot of money if you can program it. So why not? It's not about the language. It's about also there. It's about all things around it. But this
Andreas,
was my.
We are going now to show you a little bit of the makers in this group, what they create with the ESP32 chips and FORTH, of course, if you like.
Because as I mentioned, I'm very interested mostly in projects and the ideas. That is what what moves the world, in my opinion. Perfect.
Well, we have Jan Langevaad, who is going to show us a little bit of his simulator, MC6800. Hello, Jan. Can you show us a little bit of your work? You are muted. And unmute, please.
Okay.
Yes, now.
Okay, that is working, and you can see a black terminal window. Can you see it, Peter?
Yes.
Okay,
yes.
Good. I made an emulator in ESP32forth, and I just should use a little time to say, why on earth do I do that? And like Andreas, I'm a radio amateur too, and have been working in digital for many years also. So we have something in common. Back in 1975, I read an amateur magazine called QST, and they told here that you could buy a microprocessor rather cheaply. And it came with manuals and some chips and the printed circuit board. Here are the manuals, and they are very important now because when I have to write the emulator, I have to dig into those manuals many times and very, very deep. And this manual here is describing how the operating system is working on the Motorola chip, and the amount of random access memory it uses is only 0.5 kilobyte or something like that. Very, very small. And if you don't know, the Motorola M68 chip is an 8-bit chip and has 16-bit addressing. And it ended up like this. This box I still have, the computer is in here. And this is something like 5 years after I started. And we are maybe in the beginning of 1980s. And I bought a 16 kilobyte memory board. And I have a dual tape station for input and output and data. And Andreas maybe knows what that is. That a radio teletype modem, so I could write on the amateur radio bands and communicate with other people doing writing forth and back between our locations. So that is a modem, but not used on a telephone, but used on the air. Here is the card with the Motorola chip here, and the monitor is in here, and it has a parallel port. It uses this bit banging to communicate with the terminal, very complex. And here's a 16 kilobyte memory board. But the good thing is now that the whole processor and everything else can be in one ESP32. And when my hardware didn't work any longer, I was missing fooling around with the Motorola chip, and I therefore created an emulator in Delphi on the PC. So I've done this project once before in Delphi, and now I'm doing it in FORTH. And here it is, the ESP32, and you can maybe recall the box. And inside it's very slim now, only one small board, and it has a lot of memory. Memory was very, very expensive at that time. The 16K was a small fortune, and now for nothing I get 64 kilobyte of RAM just inside the chip here. And Peter has made it possible, Peter Forth has made it possible to have a disk now. It's not 100% completed, but I guess pretty soon we'll have access to as many gigabytes as we want. No problem getting input and output. So this SD card interface is replacing the dual stage tape station here. Okay, that is the hardware. The processor itself has a reset interface. It has halt, non-maskable interrupt, and it has an interrupt line also. And I have put those lines from the processor out to the front panel here. Of course, this is not on the ESP, it's just switches I'm reading digitally in the emulator. And here's how the emulator works, or rather it is how the Motorola CPU chips work. And normally when it started, it goes down here, fetch an instruction, execute, up, fetch an execution, and execute, unless there's a halt situation or an interrupt for some hardware or from some software. So that is how it's looping around doing fetch and execute. The next step after the blue box is working is to implement this one. This is a very popular Altair computer, this time built on the Motorola 6800 chip. And I've started working on that too, and it's going to be put in here. So when the other stuff is working, this hardware will be replaced by an ESP32. Okay, enough about pictures. Let's see just a little. In fact, only today I made it possible to run a Motorola program on the emulator. It's running the MicBook. Maybe you remember from one of the manuals, there was a small operating system controlling this evaluation kit, and it's only taking up something like 1.5 kilobyte. So this is the complete monitor program, and of course here it's machine code, but this is loaded into the emulator. Let's see here. So now we are in FORTH, and I have made a word called status. And here we can see the processor, the simulated processor has an A register, B register, index register, stack pointer, program counter, and condition codes. And it has used that amount of instructions loops for now. This here is the ESP, and just to be sure we are working in FORTH, here are all our words. Maybe that is new from Andreas. That are all the words we have. And up here you see all the Motorola instructions here. So let's start the emulator.
Wonderful, wonderful presentation.
Thank you. So now we're starting. That's my word that is running the emulator. And now we come to the troubles. I have some cosmetic problems here. Here should be an asterisk telling me that the monitor in Motorola coding is waiting for my command. I just enter one command, that is R. And you see, it tells me the registers and stack pointer and stuff like that. And I'm afraid that's the only thing I can do. But it's the first code I see here coming from the Motorola, the Motorola implementation. So maybe in a month or two, I can show you running basic and running assembler and other stuff. For now, I can only talk to the monitor, even with some problems. This is only, it's not really logic problems, but it's cosmetic problems. But anyway, but we can try a little. It has a command. If I enter M, that's a memory, and enter an address 1, 2, 3, 4, and sorry, it doesn't show up correctly, but I think it works. I will put in 1, 2, and 3, 4, 5, 6 into the RAM. So what we could do is leaving the emulator. Now I'm back to the fourth. And I have a small command called C low. That is, I will see the low memory if in the 64 kilobyte RAM of the emulated processor. And you can see here, I entered the numbers from the monitor into the RAM area in the emulator. That is a very, very small start, not very impressive, but it's working now. So I have to debug something like 200 instructions the Motorola can do. And I hope most of them will work. And I have a program that can run on the emulator and tell me which instruction works and doesn't work. So not very impressive what it can do, but I'm getting very close to being able to run now. That's all from here.
Wonderful, wonderful, fantastic. Thank you very much. Next presenter, very short also, is who is in a meeting with ESP32 is Pablo Reda. Do you have the computer, your R3 computer?
Yes, yes. I changed the camera. You see the camera? Yes. This is an experiment for make a microcomputer like the 80 with the ESP32 microcontroller. I use the FabGL library for generate VGA signal and get input from the keyboard. The library and the frame buffer take a lot of memory, and I make a special console with low resolution graphics for give me more memory. I will in the ESP32 FORTH R3 interpreter and for execute a program instead of basic language. This is I connect and disconnect. A phone can the words in the code. I can add numbers to the stack. I can define new words. One, two times. And now, what is different? And give me the result. Another word, counting from 0 to plus number. This one. More also how to dictionary and I can insert in memory. Execute the asking word. And for that, I have access to file system in the microcontroller. I need this the interface for sharing signal for access to memory and another program. What other program? That's all. These projects are in the in my GitHub.
Fantastic, Pablo. Very well. Thank you so much. To explain to Andreas, this is everything running inside the ESP32 chip, what we are showing to you. And who else is with the project? Ralph Lundvall, do you have the music program running?
Almost.
Hello.
I'm almost there. Can you hear me?
Yes, perfect.
Okay. I've got a loose wire here. I'm going to do the best I can.
Nice, very
That
nice.
was 130 years ago. That song was written. 69 years later, it was used on a first computer playing music.
Ralph, and you learned about FORTH recently or not?
Yes.
And
Yes.
You make these fantastic music things, and you are a musician. Explain a little bit about your current occupation as hobbyist with FORTH to Andreas.
Okay. Well, I'm retired. You can still hear me?
Yes.
Okay. Yeah, I'm retired. I'm also a drummer. Well, anyway, the music part was the first thing that interested me. In fourth, I had to define constants as to particular notes equals what vibrations per second. And then I had to make a table of length of notes. And I made it so it was intuitive as you look at the notes on the staff. If it's a quarter note, then the word was .4. If it was a half note, .2. And then I read the music from the staff, from the score, and then I enter it in. And that's about it. Oh, beats per minute, the speed is also variable. I wrote a word to allow that to happen. So Daisy, that was just played, was 240 beats per minute. I can make another one where I put in the different beats per minute and have it slow down just like the movie 2001. That's about the end of it. Thank you.
Thank you so much, Ralph. It's amazing you learned so fast, and all what you are doing in the group is also amazing. Thank you so much.
You're welcome.
Then we have probably Brad Nelson. Do you want to show anything to Andreas or to the group? Any news about development of ESP32forth?
Yeah, let me give a quick update on the things I've been improving with the system. I'll talk about three things: raw strings, some support for variants, and memory. One, if you go look at the latest version in the source code, I learned about raw strings in C++ recently. I had not realized that had gotten slipped in at some point, and so if you an interesting readability thing that doesn't really improve anything in the functionality, but if you go look at the source code, you'll now see that it is no longer just strings of forth inside of it, but is unwrapped text. And so one interesting thing for those that haven't looked in the insides of ESP32forth is that a large chunk of it is actually written in forth despite being written in C, and so there's a big gigantic string that gets loaded at start time to boot things. Thanks for some folks, I think it was a couple times back, raised that they had gotten a hold of some different ESP32 variants, and I've gotten my hands on some of those variants as well, and we've now got ESP32forth working on at least a subset of them. There's quite a variety of different boards out there. The ones that we can readily support with ESP32forth are the ones that have Arduino support, and that primarily is the ones that are dual core, at least with the Tensilica ones. There's been sort of an explosion in the family, but there's only the 32, the S2, and the C3. The C3 is interesting because it's actually a RISC-V5 inside, so that's kind of fine. But all three of those are working, and the majority of the pieces are the same. The memory map's a little different. Another fun thing, and this is one that Peter raised with me, he asked some interesting questions about the memory map because he was hearing from folks that they were running out of memory, and embarrassingly, this was not something that I had been keeping good track of. It was my memory usage with the core system. And I discovered on looking at of the 100K that I was allocating for the fourth heap, I was using up 73 kilobytes of it at start time. And this actually relates back to the system being, to a large extent, written in high-level forth. So I was only leaving 27K free out of, this is not all the memory the system has. The ESP32 is weird because it has several different chunks of memory, and they're not all together. It's also because we're running inside of a C++ program. We have to share the C heap and don't sort of have unconstrained access to everything if we want to be interoperable with C libraries. But this is the memory map, and for those that are interested, we stick the different stacks at the bottom and then the fourth heap. This is this amount of initial use is where it is now. It was more than that. So after a bunch of changes, we're down to now only 26 kilobytes used at start. I've also tried to make it more visible, the memory that's available in the system. If you go into the ESP vocabulary, there are some new words that are there that let you see the other memory in the system that you can allocate. It's unfortunately not contiguous. So if you want more memory, you can use the fourth allocate word to grab more. We might be able to do something to sort of skip over the holes in the memory map, but for the moment, the fourth heap is contiguous, but doesn't represent all of memory. I've improved my own test suite, which is mostly an improvement for me, that I'm able to run a version of the system sort of faked out without having to flash an ESP32 each time. And so if you check out the GitHub source and build, there's a large test suite that I can run sort of in partial emulation of the layout of the way it behaves on the board. This will also hopefully mean that I won't push as many bad versions for those of you that follow along with the hot off the presses versions. I've moved, part of how I got the memory smaller, I lazy load a lot of things that not everybody is using. And this is because there's plenty of flash memory on the device, and Forth that takes a small fraction of that. But the RAM is a more precious commodity. And so by using a pattern like this, with what I call a raw string in Forth, I'm able to lazily load vocabularies only when you need them. And for many of the more niche ones, like say Telnet, that means that they don't use memory unless you happen to use them. The other thing that I did is where we had this very small set of opcodes originally that were implemented in high-level code. I've gone ahead and moved them over into the C implementation. One of the challenges and one of the reasons I didn't do that originally, aside from sort of wanting to be minimalistic, is that for those of you that have poked around, there's a number of little sub-vocabularies that are used, and even things like the branching, words that are internals are nicely hidden away inside of an internals vocabulary. But unfortunately, the vocabularies were implemented in high-level Forth, and so there was a sort of a step in the boot up process where it would transition into having vocabularies. I've changed things out so that it's now possible to have words sort of live more on flash and yet be still stuffed away in a vocabulary. For those of you who've expanded the system with words, nothing changes in the interface to add your own words to the system. It looks sort of like this. But if you want to add something and squirrel it away inside of a vocabulary and have it built in, there's now a different vocabulary variant of some of the macros that are used to expand the system. And then I've moved a whole ton of words into the core system to get it down to instead of having only 26 kilobytes free, it now has 26 kilobytes that it uses, and you get the balance of what remains. Any questions?
Amazing, fantastic. Brad, this problem with the memory was pointed out by Jan with his simulator, because normally we don't use so much memory with Forth. We use very, very little memory, and nobody saw the problem, and we are very happy to. I am using now the new version, and I am very, very excited to see all the possibilities we have with this new implementation. So thank you very much.
Thank you.
Another one is Jos Ven in Netherlands. Do you have some news, Jos?
Yes, hello.
Hello.
Yes, can you hear me?
Yeah. Perfect.
Okay, thank you. I'm working on a remote controller, and the objective is to control an amplifier, set-top box, TV, 10 lights, the jukebox in Forth, an 8266 car, and one window. here's the motivation. In the past, I had to use 4 remotes. Later, I thought, well, there has to be another way. So I built an HTML interface in FORTH and was able to, and still, sorry, I am still able to control all these devices through the HTML device. But in order to control it, you must look at the screen and then hit the button. So I would like to have a remote controlled under FORTH. And that's what you see on the right. It's 3D printed and the internal system.
We can't see, we see only you talking, but we can't see the pictures.
Oh, that's a pity.
You need to share your
yes,
screen.
I forgot that. Sorry. Share screen. Share. Do you see the screen now?
Yes.
Oh, thank you. Sorry about that. This is what I was talking about. And this is the picture which I was intending to show to you. As you see on the left, 4 remotes. Present, I'm using an HTML interface written in FORTH. It runs on a Raspberry Pi. So that's on an end user's JavaForth. And then on the right, you see the remote which is under construction. It uses an ESP32, and that's the one on which I'm working. So far, the mechanics works, C-forth runs, and I'm working on the communications. Now, here you see the components. This is the ESP32. Here you see another board. It contains 2 MCPs 2307 Ting, and that basically generates an interrupt to the ESP32, and then the ESP32 sends the information to the Raspberry Pi, and the Raspberry Pi sends it to the various devices. Well, that was my presentation. Thank you.
Thank you so much, Jos. It's amazing, all your work. I have also Atle from Norway. Please unshare, Jos, your screen.
Yes, is that, oh, stop sharing, okay.
Atle has news. He is making a super expander with ESP32. I am surprised. You need to unmute, Atle.
Yeah, well, you know, I was going to. You told me I should show the FORTH mobile. Now the problem with that is that I've been working on something else, and it has crashed, and one of the cords here has come loose. So that's why I will be showing this super expander instead. Now. I have.
Can you? I have a question for you. Are you able to tell Andreas and other friends in the group in 3 minutes or in 2 minutes, if possible, what is the difference? Because you are a programmer with a lot of experience in many languages. What is the difference to program a FORTH mobile, a robot, in FORTH?
Okay, so. What happens when you compile or when you create a firmware for a rover? Let's see if I can share a screen to show it. Now, yeah, normally you have to write the code, and then you have to compile it, and then you have to upload it. Can you see me moving a strobe bar now?
Yes.
Okay. And so if there is a change of something, then you have to make the change. You have to go in and edit, make the change, recompile the program, and then re-upload it to, in our case, the FORTH mobile. Now,
so it's basically about productivity.
It's about the possibility to make changes on site. When you're out in the field, you have your robot with you, and suddenly there's a bug. Oh, it's not moving away from that stone. It's supposed to move away from that stone. And what you would normally have to do, you would have to take it home and do all these things that you do when you edit, compile, and upload, etc. But with FORTH, you can simply take that word. For example, this one clears all the switches, and oh, I had 17 switches instead of 16. Then you just edit it there, upload it quickly to without touching anything else. You upload only this single word to the robot, and the bug is fixed, and you can continue your testing. That is the difference between working. Well, it would be the same in BASIC, for example. You could change an instruction, but with FORTH is that these words are self-contained. They when you create them, you respect two vital mantras in programming about strong cohesion and weak coupling. And that you cannot, with a basic program, that's virtually impossible. But with FORTH, every word does one thing. That's the strong cohesion part. It does one thing and nothing else, single responsibility. And if you change something with this, this is something you have to be clear about the number of parameters that will what it expects on the stack must not change, and what it leaves on the stack must not change. But as long as you keep that in mind, then you can change one word completely without affecting any other part of the system. But what got me hooked on FORTH is the fact that you can do this while the robot is driving across the floor. You can debug it while it's driving.
Fantastic, amazing. And
so,
your board, and about your board, your new board.
Well, I'm gonna have to let's see how I can do that. I will point to it. You will see this. I'll show the code first, and then I'll show the board afterwards. Let me see here what I can do. If I can point to it. Nah. Well, anyway. So what this board is, it's an, if you,
do you have some pictures of your board, or?
Yes, I do, but if I can just shut off, if I can just, do this, then you should be able to see. Can you see the board now?
Yes.
Okay, so I just shut off the, I'll see if I can place it so that it's possible to see it. Can you see it now?
Yes.
Okay, and you see my screen. So here, what it does here, it reads the board, and then it reads all the sensors and it copies the state of the sensors to the output using parallel to serial for these sensors here, and then it's using serial to parallel to get out to that relay there. So what this word does is basically act as the most contrived switch you could ever imagine. So let's see if we can get it to work. So what main does 200 times, it copies the input to the output. So it reads the input, converts it to serial, and lets the ESP32 get hold of it. Then the ESP32 converts it back to parallel and sends it out to the output registers. And here it does. Now let's see if, so this one is manipulating an output, as you can hopefully see. Can you see that?
Yes.
Okay. And this one is manipulating the relay. Did you see that?
Excellent, I see, yes.
Okay, and now it doesn't work anymore because main has finished. So I have to run main again for 200 times, and then it will act as a switch. That's probably the most contrived switch that has ever been devised. So this is what I've been doing with FORTH and KiCad. And of course, the flagship application for this is the blinking lights. So that's what I've been doing.
Very nice, Atle. Thank you so much. I am the next one. If you allow me to share my screen. Atle. And share so I can.
Didn't I just unshare my screen? I thought I did.
Okay. I see you, and I will share my screen now. So can you see me?
Yep.
I have here the, oh. Hello. I can.
Peter, I see a thing that says Peter has started sharing screen, but I don't see your screen. Oh, there it goes.
No.
There it is. So, Peter, we can't hear you right now.
Now?
Yep. Okay. I'm muting all the others so we don't get these echoes.
So I have here, I only want to show you the SD card words I was doing these days. Here you see the ESP32, the poor man adapter. I have also the professional one from Arduino, but it's having some problems. I have here the Arduino monitor. So you see when I press OLED init, we have here the OLED working. And if I do, I was preparing the presentation, SD directory. You see my files here. And I can dump a file, one of the files, for example, this one, fix update fix up that. This is here the file. And we have also new words for reading the card. We can delete files, we can create a directory, we can remove a directory, append a file, read from a buffer, write to a buffer, and many other words. I am working with this. And you see here, the next project is the DHT11 temperature sensor. And some of the members in the group were asking for the GPS. Here's the GPS card and the antenna and the card here. And you see also the ESP32 on the FORTH mobile with, I have in front here the OLED, the compass. I have a gyroscope. Here is the gyroscope. And I presented end of year the MOSFETs attached to the ESP32, and here is the other card, the professional, the Arduino. I had a bit of problems with this card, so I decided to create my own version. I will publish this in this week. I was testing with different sizes, with very small cards, old cards, and the new ones with gigabytes, and it works perfect. So I am very happy and thankful to Brad. And this is everything. So in future, I create another presentation, but this is what I am doing in this last weeks, what I was doing these last weeks. So Ulrich, if you want to continue.
Yeah. Okay. Thank you all very much about the presentations on ESP32forth. And yeah, we will have a look at the Fignition. Julian Skidmore is our next speaker. Julian, are you ready to do your presentation?
I could be. It's quite possible.
Great.
So
please go ahead.
So the presentation has been, I've produced it quite recently. Let's see how it goes. So I'm going to try and share my talk, see if that goes okay. Can you see it?
Yep.
Hope you can. Right. Okay. So I'll start playing it. Okay, lovely. So this talk is called Into Fignition, its purpose and architectural decisions. So my name is Julian Skidmore. I have a BSc in computer science and a MPhil in computer architecture at Manchester University in the Steve Ferber research group. And Steve Ferber created the ARM processor, although I don't use the ARM processor in here, you see. Sorry, Steve. So anyway, what is, you may have seen a picture of Fignition in the past, and Fignition is a rather simple computer. It uses an AVR processor with either 16 or 32 kilobytes of flash memory, and the flash memory contains the operating system, the virtual machine, and the compiler all in one go. It also contains device drivers for the 8 kilobytes of external serial RAM, which runs user programs, 0.5 megabyte of serial flash, which stores all your code, user code, a keypad with which you can type programs, and this keypad, it is a bit of a chordal keypad, so that combinations of keys can give you like a full set of keys across the keyboard. We
Julian,
also support.
Sorry to interrupt you. We're seeing your presentation screen and not the slides. Well, we see parts of the slides, but we actually see the presentation screen, the presenter screen.
Oh, right. So you're seeing the next screen as well as that?
Yeah,
oh my goodness.
We have the slides on the left and the current slide, but not the.
Oh, right. Okay.
Yeah.
Fair enough. So if I stop the share, right, and then I reshare it, and I share that.
Probably the other screen.
Is this a bit better?
Yeah, we see a Jupiter ace.
Oh, wonderful. That's really cool. Okay, so now it's a bit bigger then, isn't it? You can actually read stuff.
Yes.
That's good. Yeah, I've never done a presentation over Zoom before. So, yeah, so I didn't realize that it would do both. So there we go. So Fignition has a CPU which does everything, apart from the user programs, which are in external RAM, flash, 0.5 MB of flash for storing user code, a keypad, as I've just described. It does composite video out of its video connector, and it does simple PW audio out of the audio connector as well. It's got USB, but that's only used for upgrading using the wonderful bit-banged VUSB software driver, which is quite amazing. And it uses it for powering the computer itself. So Fignition is primarily influenced by the wonderful Jupiter Ace computer, which again has a bit of a ZX Spectrum type character set. I'm also quite significantly influenced by Andrew Holmes's Mark I TTL fourth computer, which implements virtual machine primitives in its internal microcode, and has a ROM for the actual FIG-forth implementation. So I took quite a bit of that for my initial version of the Fignition main code. Also, I'm quite influenced by the ideas in computer architecture, a quantitative approach. Hennessy and Patterson, that's the second edition. These guys created RISC architectures. And finally, of course, Brad Rodriguez, Moving Forth, which is a really excellent book on describing the most important aspects of how to port forth to a different processor, where you should place most of your effort, where it's going to be the most efficient way of implementing the language. Okay, so all of these kind of influences went into Fignition. But a bigger question is this, is why did I design it that way when I could have based it, when I could have based Fignition on a single chip AVR that had far more flash than the 16K that I started off with, and far more RAM, and it would have accessed the RAM much more quickly. Why did I base it on 3 chips rather than 1, or even go a step further and say base it on a 32-bit ARM processor? And the answer is basically that I want to get rid of the magic. Fignition is really an educational computer. I'm not trying to sort of track satellites. I'm not trying to reproduce a remote control. I'm not trying to control a robot on Mars. So what I'm trying to do is make a computer less magic. I want people to be able to see the components, and I want it to be understandable from the very highest user type level all the way down to architectural sort of low level stuff, because I believe that that's empowering. And here's an example. Here's a 9-year-old girl, and she soldered together a Fignition computer. This is way back in 2011. She's an adult now. She's probably at university or something. So, she painstakingly did it with the help of her dad. Well, no, she did it by herself, but under the guidance of her dad. And then when she'd built it, she switched it on, And you can see the look of delight in her face, like she's actually built a computer from scratch and it worked. And who can say they've done that? So few people have built like a self-contained working computer from scratch. And that's what it's really about. It's about empowering people. It's about getting them to the heart without the magic that sort of obscures so much of computing today. So let's look at some of the architectural decisions inside. And the first thing is, let's look at the memory map. So in Fignition, okay, from the viewpoint of Fignition, when you're running Fignition, the memory map looks like FORTH ROM, which starts at 5E38 in the latest firmware. And then that's an internal flash memory on the AVR. And then you've got the external RAM, which is mapped to 8000 in Fignition's address space. And for the an 8K RAM, it only goes up to 9 FFF, and after that there's 3 shadows of 8K RAM. And at the bottom, the primitive tokens, the sort of like the basic command set for Fignition, that occupies the space from 0 to 0000 to hex 49. So why does Fignition work in this way? Okay, so Fignition is unusual in that it is a token-based forth. It works with 1-byte opcodes, or it works with 2-byte opcodes, which are colon definitions. So because it's done in software, I can just follow colon definitions straight after tokens themselves. So I don't need to use like a single bit to identify which are colon definitions and addresses, in the same way that, say, the J1 or the Novix processors would have to do. And the reason I do this is because SPI flash memory is slow, and therefore it's more efficient to actually be able to do a significant amount of processing per byte than to have to read in 2 bytes, even if you could use multiple bit fields. Okay, basic insights into computer architecture say that there are a small number of commands that are executed frequently, and this follows a sort of power law, particularly small literals, especially 0, adds and subtracts, conditional and unconditional jumps form the majority of instructions executed. Now, Forth has often, by many measurements, slightly different kind of sort of popularities of various words and definitions. Here, in this example, call and exit are the most common ones, because mostly because definitions are quite short, and therefore there's a enormous proportion of calls and exits. But nevertheless, simple operations dominate over more complex operations. So let's look at a simple program called Snile Mover. Okay, and for this, I am going to, first what I'm going to do is I'm going to switch back at this point to like using a single screen. I'm going to point my screen at my actual Fignition. So this isn't just a dry presentation. We have a real Fignition to play around with. And I'm going to take off my jumper. And underneath my jumper, I have my Fignition t-shirt. So there's a merchandising option with this actual presentation, and also my amazing drink from my Fignition bottle as well. Lovely, lovely Fignition water. So I'm just going to move my Mac, and hopefully I can make it point at, oh yeah, don't need that. I can make it point at my Fignition computer. Okay, so is that visible? Is that usable? Oh, sorry.
Yes.
Can you see that?
Julian, perfect.
Yep.
Okay, right. So the first thing I'm going to do is I'm going to type out the get the character set on the screen, because Pablo earlier showed his character set. So I will show it on Fignition too. So right, and I'm just going to be a do loop. I emit loop semicolon, and in Fignition, in the Fignition editor, I can just edit things as I please. You see, so it's all it's quite interactive in that way. I press Shift Enter to enter a line, and it's compiled that. And now I can say type, say 9732 dot chars, and it should display it. So that's the character set. But I have a full character set, and if I have higher numbers, it should actually display the whole thing. Whoops. There we go. And lo and behold, we have lots of block graphic characters, just like Pablo's version of his character set did. We also have an interesting pair of characters just here, which I call the snile. And so we're going to write a little program that moves it. Snile mover 23.0 do 25.0 do I at 32 emit 30 emit and 31 emit dupe pause loop oops loop. Oh no! Oh, this is really bad. The Fig keys driver is hung. Right, let's try again. Okay, let's try again. Fignition. Right, I can do cold as well when it works, and I can see the logo popping up. So there we go. Let's try again. I'm just calling it snile mover. 23.0 do 25.0 do I at 32 emit 30 emit 31 emit dupe pause loop drop semicolon. Okay, so hopefully this will compile. Right, and it did. And what I can then do is I can run it, and I can insert a pause beforehand, so I can make it pause with 10 frames per each one. And that is not correct either. Wonderful. Great. This is what you get if you don't test your demos beforehand. Right. 23.0 do do I 25.0 do. So that's the row. Sorry. I over at 32 emit 30 emit 31 emit dupe. I don't want dupe. I have to do something else. I'll just make it 10 pause. I'll make it much faster actually. 1 pause. Loop drop Oh, it's hung again. Oh no, it hasn't hung. Right, loop, okay. Drop, semicolon. Right, okay, so now I can type in SM and hopefully it'll be a bit better. Oh, there we go, that's what's intended. A little silly bit of animation that shows a snile moving across the screen all the way down to the bottom. So I'm going to return to my presentation. Okay, so if I share the screen, can you see my screen? Oh, it says, were you actually just seeing it in a little half of the screen instead of the whole thing? And were you seeing this side by side all along?
You can slide between the two, so you can zoom in on the...
All right, so you can see both now, can you then? You can see my presentation now. Okay, lovely. Okay, so Snile Mover, the simple program that I tried to show and eventually kind of got right. You can see that when it's compiled, mostly it's just single byte tokens. So of the 20 or around 30 sort of commands in there, we have mostly 20 single byte tokens and 7 single byte tokens with 1 operand and 1 instruction that's an actual address, which is pause, and that's at 6EF1. Basically, the reasons for this is because it's normally very slow to read from SPI RAM if I have to read. If I have to send a command, an address, and read a byte every time. But I find that I can improve the performance up to by a factor of 4 if I am able to read successive bytes from SRAM. And this is a principle called locality. And it works because jumps are relatively infrequent compared with sequential execution. Now, for Fignition, of course, one of those commands, the 6EF1 command for pause, is in fact inside the ROM. But because it's in the ROM, you still don't need to make any more SRAM accesses. So we can still, when we finish this command, pop out and carry on sequentially executing from SRAM. So that's the first thing that Fignition does to speed up the performance of its virtual machine. The second one is that it uses pipelining. So this became common with RISC processors in the 1980s. And we use the SPI peripheral in order to perform pipelining, while the SPI is reading out 1 byte from RAM. The processor is, the AVR is executing the previously read out byte. And so we can overlap instruction fetches with instruction execution, even though I'm just using a serial processor. Now, one of the things is that all my optimizations are really a product of a really stupid mistake I made at the beginning of the development of Fignition. I went to Maker Faire and I boasted that Fignition would execute at 500 kips, and Maker Faire was in Newcastle in the north of England, where it is wet. I boasted that I could do 500 kips out of it, and then the BBC got an interest in this, and so it got featured on their website, and so then I had to kind of fulfill my objectives of getting to 500 kips. So I spent a lot of time trying to improve the performance, which most people with the ESP32s probably don't have to do. So in addition to what I've just said, I also created a branch target cache for Fignition 2 to improve the performance. And the way this works is as follows. Normally, the biggest hit that you're going to make when executing code on Fignition is when you have to make a branch back to some earlier code or branch forwards. And in later architectures, processors cache the branch target so that they can avoid all the stalls that they would have fetching that data from RAM. Okay, and the first thing that we do with Fignition is that branches only use 1 byte, a 1 byte relative address rather than 2 bytes for the full address. And that means that we can improve the performance by about 20%. But also what we do is we cache the very first byte that would be the target of a branch in internal RAM. And this means that it can be executing that instruction while it is fetching the next byte in the code. And that improves, again, the performance by another 20%. So that finishes the direct presentation into what Fignition is and its purpose. Its purpose is as an educational computer, and it's meant to be understandable from top to bottom. And there are a number of architectural decisions I've made that improve the performance beyond what you might expect from some serial RAM. So the last thing I'm going to show is a little demo that is a bit better than the Snile Mover one, and shows some of the relative possibilities with running little programs and things like that. I wrote a floating point, software floating point for Fignition, and Fignition can also support high-res graphics by reading the SPI RAM. It is actually fast enough to support high-resolution bitmap graphics. So if I take the Mac back to this and I stop the share, hopefully you'll get a full screen for being able to observe what's on the Fignition screen, and I will be able to type. So I wrote a little program a while back that shows the Lorenz curve on Fignition, and this is it in block 100. This is the first page of it, and this is like the full screen editor I use with Fignition, so I can edit things here and there. I can also copy and paste and that kind of stuff. Whoops. Oops. I want to quit. There we go. And there's another couple of pages of this code. So there's the next two commands just here that evaluate more of the Lorenz curve and plot it on the screen. And finally, I put it all together in a function called .los, which runs in high-res mode. So quit this, I can now load it. And to run it, I have to type in, what do I type in? Oh, here we go. Right, I have to type in there we go, and it generates a Lorenz curve and does it quite quickly. It will do it substantially faster, for example, than a 68,000 based Mac Plus, even though that has a 32-bit architecture and Fignition only has an 8-bit architecture, which is a way of showing that even an 8-bit AVR processor is more efficient than an early 32-bit RISC processor. So here we go. It's quite wonderfully mesmerizing is the Lorenz curve. So there we go. So that's, were you able to see all of that?
Yeah, great.
There we go. So that's my presentation of Fignition and a bit of a demonstration. I hope that it was satisfactory.
Thank you very much.
Fantastic, Julian.
I think we have time for some questions. So are there any questions to Julian?
You were saying that you had like a corded keyboard. Can you explain that, or was I misunderstanding that?
Yeah, that's correct. So what I wanted to do was I wanted to be able to demonstrate how matrix keyboards work, but I didn't want somebody to have to spend ages and ages soldering in 65 of the sort of little buttons or whatever, just so that they could type a program. So a 2x4 embodies the minimal amount for like a matrix keyboard, and combinations of these keys allow you to type on it. Now, if I take my Mac back to here, you can see that the Lorenz thing is continuing quite happily. So I will unplug it and start again with Fignition, because I'm going to have to take apart the unit itself. Okay, so if you want to be more efficient, you can use Fig Keys, which is a PS2 adapter for Fignition. The rest of the time, or how it's originally intended to run, is it going to boot? I want it to boot. Here we go. Shall we try again? Here we go. So we boot. So it's a bit awkward to try and show it like this, but basically the idea is that you can hold 2 keys down at a time. So some of the basic functions like key presses, like space, for example, that's a common function. So that's on the just a single key by itself. Delete is also very common. Return is quite common, and cursor keys are quite common as well. And this is a shift key. So, but if you hold down one key, you find that it'll give you a prompt on what the other keys will do. So top left and some other keys gives you numbers.
I think you're
and similarly, if you hold,
I think you're holding the hardware right over the part of the screen that I'd like to see. Thank you.
Okay, yeah, I got to show both, haven't I? So, yeah. Right, okay. Can you see it now? Can you see both now?
Absolutely perfect.
Okay, great. So, if I hold down, say, this key, then it gives me a prompt for the other letters. That's to help the user. And then I can press one of the other 7 keys and get some more of the alphabet. I can do shift, and then it would be capital letters to do the same thing. I can move the cursor across, insert a few spaces, and that kind of stuff. So, and I can also do symbols in the same way. So if you press shift and then hold the key down, you get symbols instead. So for example, I've got like some shaded characters just there, or I can type in a copyright symbol or a question mark or things like that. All right. Yeah, and like a pound symbol and that kind of thing. So yeah, so you can get the full set of characters from the keypad, And when you're used to it, it is actually quite fast to type on the keypad itself. If I go back to facing people, no, oh wait, you don't need to see my face, that's not important. So the real problem with the keypad is that the tack switches wear out quickly. They get dust in between the actual inside of the keypad, inside of an individual switch, between the dome and the contact on the other side. And this means that after a while, probably maybe a few months or something, the keys will start to become harder to press. You'll have to, instead of just pressing the key down, you'd have to wobble your finger across it so that it would do it correctly. So if you've seen any of those TV programs, so the YouTube videos about where you can build your own pet computer or something, and it has loads of tack switches on it, or a DIY computer with tack switches, it would have the same problem. Dust would get in between, and sort of relatively quickly, the keyboard would start to fail. Anyway, thank you for the question. Does anyone have more questions?
I would like to make a comment, if I may, just to say how much I appreciate the idea of de-obfuscating the computer industry. It's,
thank you.
It's a pet peeve of mine that people seem to try to make things as complicated and obscure as they can. So thank you very much for working the opposite direction to make it simpler.
Yep. It's okay. It's a pleasure. Thank you. It's appreciated.
I think I want to make a comment as well. I could have used a teacher like you when I was a teenager.
Oh, thank you.
Right. Yeah, so it helps a lot to dig really to the bottom and to get a thorough understanding of what's going on. And so for me, this was also the enlightenment when I did some digital computer things and wired up in ALU to understand what this is all about, and all of this sudden says, this is how things work. So that's great, and Fignition will hopefully help many children to actually find this out as well.
Yeah, I managed to sell about 1,000 Fignitions over over the period, like 2011 through to 2014. Some of them did go to, like, the University of Strathclyde, used them for first year projects over for a couple of years. A couple of schools used them as well, and they were available from RS Components too until they ran out, which was fairly recently.
Mm-hmm. Okay, any additional questions? So that doesn't seem...
Can I say one more thing?
Sure.
People are asking about the keypad. If you go to, if you just Google sites Fignition, it's a Google site, then part of the sites for that will show you the entire keypad layout mechanism, so that you can see how all the key combinations work.
Mm-hmm. Mm-hmm. Yeah, also inside there. That's great. Right. Any additional comments, questions?
Yeah, I've got a question. Philip
Sure.
Eaton here.
Go ahead, Philip.
Yeah, your performance claim of 500 what was it? Instructions per second, 1,000 instructions per second. How can you put that into some context? What's the processor speed, and how would that compare to other CPUs? Because that number's, I mean, it's not MIPS. I know I've heard of MIPS a lot, but just give us some context on what that number actually means, please.
Okay, 500,000 instructions per second. So in the early, well, the late 1970s, a typical processor used in a microcomputer would be a 6502 running at 1 megahertz. Now, the maximum instruction rate for that is 2 cycles per instruction, so it operates at 500 kips max, 500,000 instructions max. And I wanted Fignition to approach the speed of a real hardware microprocessor of the day.
Technically, it's a half a MIP, right?
It's half a MIP, yes.
Yeah. Yeah, very nice.
0.5 MIPs or 0.1 MIPs in binary.
Yeah. Yeah.
And sorry, just to add, so what's the processor speed? What's the megahertz of the processor itself?
So the AVR is running at 20 megahertz, and that means that on average, well, at best, it takes about 40 clock cycles to execute a single fourth primitive on the AVR, which, considering the constraints, I'm really happy with.
Great, thank you.
Yep, great, thanks. Thank you very much for this very interesting presentation of your great project. So I think that many of us enjoyed this quite a lot.
Oh, can I say one more thing?
One more thing.
There is another thing. Just one more thing. Yeah, thanks. Like, there's another reason why it is like 400 kips or 500 kips, and it's because it's generating the TV display in software, and that takes up half the CPU. So really, you should think of the AVR as running at 10 megahertz, and then it's taking about 20 clock cycles to interpret a single instruction. So yeah, I've just doubled the performance of it in your mind. So that's really great.
Right. So yes. Is a kip a fourth instruction?
Yes, it's 400,000 fourth instructions per second. That's its maximum speed.
Okay, good to know, because it could have been processor instructions, and that's sort of directly related to clock speed, isn't it? Whereas what you're saying is there's a lot of other stuff going on as well. And I mean, just as a bit of background there, I'm working with my 6809 based Vectrex system, and almost all of the processor time there is spent writing vectors to the screen, because that's what it, that there's no coprocessor or any buffers or anything. So I know exactly what you're saying. It's tricky.
Yeah. What we already experienced with Sinclair computers, they did also video generation in software in the slow mode, and then you can switch it to fast mode, so avoid that. Yeah, maybe that's something for Fignition as well, to speed it up. I don't know.
Oh yes, of course, it's inspired by that kind of approach to generating a TV. One thing I do though is that Fignition uses its timer hardware to automatically generate sync pulses. I can execute a few instructions on either side of it, every horizontal margin, which a ZX81 could not do.
Yeah, and even in I don't know how you call it, in the blank, when you refresh in the synchronization line, you can execute things as well.
Is vertical blank?
A vertical blank, yeah, that's what I mean. Yeah,
there's the front porch, and I think the back porch, and that kind of thing.
Yeah, great.
Thank you very much for listening.
Thanks. So let's see. We proceed in our program and schedule. As you might have read in the schedule, Brad unfortunately had to leave, so we shift his talk and presentation to next month. But a computer that many of us as children had first encounter with was the Gameboy. And even though it was mainly used as a gaming engine, and now we can also see how it will be programmed in FORTH. So Thies will talk about making games in FORTH on the Game Boy Advance, which is a later model, not the one that I had initially. But Thies, are you ready and can give your presentation?
I am ready.
Great. So please go ahead.
Let me share my screen. Can you see it? Can you see my screen?
Yeah, again, we see the presenter's view.
Yeah, I just wanted to make sure.
Yeah,
okay,
well,
cool.
that works.
Now we go up. This is what, okay, here we are. Yeah, hi. Yeah, so this is about Game Boy Advance programming in FORTH. It's a bit of a rambling talk. It's not very deep programmer. It's not a very deep talk, but this is more of my journey of cobbling things together to be able to program in FORTH on the Game Boy Advance. A little bit about me. So I'm now a compile engineer at ARM. Actually, this is just me being an ARM fanboy. This has nothing to do with me representing ARM, of course. I think that's maybe a bit obvious talking about something as early as the Game Boy Advance. I live in the UK. I am from Holland, and yeah, that's it. So let us. Just a brief overview. I think those are sometimes handy to have for the talk. So I start off with like why I wanted what I wanted, which was this system, then exactly what I wanted, and maybe there's even a resolution. I'm trying to make it exciting. I'm not really sure if that's going to work out, but let's see. So in the beginning, I started off programming for the Game Boy in C, but a while later I started programming actually for this thing. This is a DS, which is the successor to the Game Boy, which is fairly similar actually. It has a ARM9 next to the ARM7 that the Game Boy Advance has, and some other things, but like the way to programming is basically the same except for the additions that the DS gave. I started programming that I was interested in sort of the basics of programming a little bit, as you guys all also are probably. So I sort of messaged this guy at some point who had written a thumb assembler in Common Lisp. I'm more of a Lisper, Common Lisper. I self-identify as a Common Lisper maybe. And that was very interesting, and I expanded that to also be able to handle ARM mode and give it some other features. And I thought, what can I do with this? And I didn't really know, and I wanted to understand programming languages a bit, and I thought, oh, maybe I should write like an interactive Lisp system on that thing. And before really I got anywhere with that, I moved actually from Sweden. I was living in Sweden at the time, and I was on mailing list with Lars Brinkhoff, I think, as well. Which I thought I remembered that name, and actually it is from that. I followed another Lisper actually to Nepal, where okay, no, okay. And there I was bashed over the head left and right with FORTH for some reason. So first of all, I went there for this project called One Laptop Per Child. I don't know if you guys heard about it. This was like in 2007, 8. Is like these little laptops. I can't see myself on the screen, but I hope you guys can see it. Which a local organization there implemented. And the fun thing about this thing is that the firmware is in open firmware, which a lot of you guys probably know about. So I can start it up. If you boot here, you can see it instantly boots into open firmware. I can just type something in it, which will make it a bit clearer, because it has Pong on it. So I don't know if you can see this. Here. So this is Pong in open firmware on the XO laptop. Has nothing to do with Game Boy Advance, but I thought it was an interesting device. I don't know how many people know about this device and that it has FORTH on it. And my friend who I went to this project with, Lugori, I guess Lars at least knows about him, Lars Brinkhoff. he was into FORTH. He had been programming in it for it with a bunch of buddies. One of those buddies, he gave him FORTH for Professionals, and I don't know how common that one is. How many people know about it in the English-speaking language? Apparently, it's translated from French. I'm sure you guys have a much better context for this, but and it was translated to English, and I've tried to find it since, and I can't actually find it. But I made a copy of it. I Xeroxed everything, so to speak, when I was there in Nepal. And there, I also for the Nintendo DS, I transcribed JavaForth, which is this really nice FORTH system, which is sort of a learning FORTH system with lots of annotations on it. And that was really interesting. And what I also had was this thing called the DS serial, which meant that you could put a serial interface into your DS and you could do interactive things with it. So I thought, that's wonderful. I'm going to do that. I'm going to make an interactive FORTH system on a Nintendo DS. And unfortunately, that failed because A, there was lots of other things to do, and B, I didn't really understand how low-level programming actually worked. I put in an address at some point, but I didn't really understand how that should be translated into actually running it on the system itself. And there was not a lot of documentation because the internet was like not really like forward with a lot of information. So that just sort of fizzled out. And I always thought it was a shame. So there was darkness for about like, I don't know, how long, 12 years or something like that. So on that picture is the DS serial. And I was always said, I can't find that anymore. And I was always said that I never moved forward with that anymore. And then in lockdown, in Corona time, I got more interested in first just in hardware hacking. So let me see if I have. So there's like lots of these boards jumping up right these days, right? These FPGA boards. So this is like a funky board from a group in the Balkans somewhere with lots of bells and whistles. Very interesting. Also an ESP32 on here, by the way. Lots of other things as well. And so I started looking into J1 FORTH, which is actually sort of a hardware learn how FORTH is implemented kind of thing, I guess, which I never totally grokked, but that got me thinking, yeah, right. It would be interesting to pick this stuff up again. So I thought I'm going to do that. And Gameboy development community, there was a Gameboy development community that was picking up. And so there's, like these days, there's more and more going on, I think, in sort of like half embedded space of olden video consoles, which is just fun, low level programming. And so I needed certain things to get this thing on the road, which is I needed a serial connection to my Game Boy Advance in some way. I needed a FORTH, and I needed some kind of project to actually do something with this. If I'm going too quick, please tell me. Maybe I'm talking too quickly. I'm just conscious of time. First, a little bit about Game Boy Advance internals. It's also really interesting to just hardware hack the Game Boy Advance, by the way. It's a very simple system, but it has, like, you can see on the page here, that it has all of these contact points, which are test contact points from the factory. So they tested these Game Boy Advances by just pressing against those test contacts and just running like their whole program over it, which is really, and they labeled everything as well, which is great for people that like to tinker with this a little bit, because it makes it very obvious where you should put these things, and it makes it very easy to just solder wires to it, whatever. The old Game Boy Advance was a 4 MHz Z80, and then the Game Boy Color was a Z80 that ran at 8 MHz, I think. Don't quote me on that. But the Game Boy Advance is a totally different system. It's a 32-bit ARM 7 TDMI system, which runs at 60 megahertz, somewhat underclocked, I believe. And it's just a very nice system. It's sort of the last of the Mohicans, so to speak. It has just a very simple 3-stage pipeline, just fetch, decode, and execute. It has no caches, no MMU, no nothing, no interface between you and the hardware, which is sort of the connected consoles of the day that were 3D, like the PS1, the Nintendo 64s. This was in the time of the GameCube as well. Like these were starting to run through access layers, but not the Game Boy Advance. Like everything is registers. So you have full control for everything, and you don't have to think very hard. This one, the Nintendo DS, starts to flub around with caches, which makes programming in a way more interesting, but a bit more annoying and opaque. And it's actually horrible to program for in a certain way to get performance out of it. This is just easy peasy. So it's actually a really nice sort of embedded device that you can program for, because it has buttons, it has a screen, it has sound, it has a serial port. It costs $30 or £30 to buy, which is not that much. So yeah, and people are interested in it. It's shiny, it's interesting, and the way that you program them is basically you buy like a flash card, and you can just flash something on here. There's different kinds and varieties, so I won't go into that. Yeah. So what I needed was some kind of serial port. And serial communication. So there's lots of documentation on the Game Boy Advance. But oh my God, can I move this thing? Sorry, the screen is over the. Wait, maybe I can just move it like this. Right. But the serial ports are really not that documented, because normally people write emulators for this, and so anything that you need for emulation is fairly well thought out. But things that have to do with hardware, people just have not bothered with that very much. So there's lots of different modes on the Game Boy Advance for serial communication. But so SIO. I don't know if I did the right thing. Right. So you've got like normal mode, multiplayer mode, Joy Bus mode, which is connecting to the GameCube, because it can talk to the GameCube. But what is here? We've got a UART mode, which is great, but it wasn't very documented. So it took a bit of time and some programming with an oscilloscope to understand what was going on there. And it's actually like a straight up UART mode, which is great. So I wrote a little setup for that. So basically what you can do is you've got a USB to UART cable, which you can just buy, and then you can put that, you can bridge that together to there's like these Game Boy Advance serial cables, and you can, as long as you know what the wiring is, then you're golden, and that just means a bit of faffing about to understand what actually goes where. That wasn't that hard to figure out, luckily. And then I can try to make this work. So I've got a Game Boy Advance here. I plug it in. Hopefully this will work. I'm not sure. You start up your Game Boy Advance. Let me start the program. So this is like a test program that I made, all in C, nothing in FORTH yet. We'll get there. We'll get there. So basically, this one is now waiting for serial communication. And on the screen, you can see that the command line. I hope it's big enough. I don't know. I just moved to OS X, and I'm not really sure how things work on OS X. One of those shiny silicon things. So I press a button, and I write something. I don't know if this works out. So blah. Don't know if you guys can see it. I've got no idea if this works. I don't know if you can see it. It works. That is nice. And so you can do like fancy things with that, like if you want like to put like a background on it, for example. I hope this will work. Boom. It works. So you can just directly send stuff to your console, which is already like a big win compared to like the standard way of compiling and then loading it onto your ROM and then loading it on your device, which is just like a hassle. You can do it in emulation as well, but that isn't always what you want, because emulation doesn't perfectly represent what's going on. Okay. So that worked, and that was nice. Let me. Oh, how do I get rid of this thing? Oh, you can move it. Yeah, somebody else said that as well. Yeah, and then I needed the forth, and it's too bad that Brad isn't here. So I had this forth based on the Jones forth, but the problem with that is that it's its own like little world, like it's straight assembly with a custom assembler that has nothing to do with any kind of toolchain. And that's nice, but there's also like that means that you need to write everything from scratch, and so you can't use sound libraries or whatever. And it's actually handy to interact with that. So I just Googled to see if there was something out there, and there turned out to be something out there, which was great, which is from 2005, something called PandaForth. So some person put a forth system onto this general Game Boy Advance website with demos and lots of stuff. Left it there. Nobody has touched it since 2005. I tried to run it and just a couple of changes to make the toolchain work with the modern toolchain. So for the Game Boy Advance, you can just use your Game Boy. The ARM7 TDMI is still supported by modern toolchains, which is great. Which is kind of so ARM-V4 is still the last, the earliest processor that's still supported by both GCC and LLVM. Yeah, and so that wasn't very hard, and that worked. And then I looked in the source code a little bit, and then it turned out that it's actually CamelForth. So what this person has done is they translated the Z80 implementation of CamelForth to ARM, basically to ARM assembly. So they made a couple of assembler macros. I've got those in the here. So basically, the top one that's commented out was the standard move implementation, which basically is a transcribation of the move that was in CamelForth. And the nice thing about it is that this person made so BDOS on CamelForth. I'm not really sure if that's like a standard forth word. Is the interface to the operating system, and what he did was he made it the interface to C. So it just calls out to the ABI, or it lays out stuff in a way that the ABI can understand, and the ARM ABI, and then a C program can pick it up on the other side, and that works quite nice. So this particular forth and C have nothing to do with each other, but he just made like a nice interop. Yeah, and then I needed a project, and it turned out that, as I said, the Game Boy Advance scene has climbed up. I think because maybe people that used to fav with Game Boy Advances are now coming at an age where they think like, oh, I want to do something with my Game Boy Advance anymore. No, that's actually not totally true. There's mostly it's younger people actually that do this. So scratch that. The last Game Boy Advance proper jam that we could find was 2004. So that was also a good long way off from this Game Boy Advance competition. So that was a fun way to play with a fun project to have to focus like my development on. The interesting thing about games is that like this ARM32 chip, like 32-bit chip, has a lot of like is fairly powerful to a lot of other systems, but like for games, like you can always go better and faster, and that's what's like these things like push your system to the limit. It's got a 60 frames per second refresh rate. It constantly needs to update the sound. Your logic needs to be updated, usually on a frame boundary, although that's not necessarily necessary, but that's usually expected. That's the standard. And FORTH is not necessarily like the most perfect fit for that, because so for example, this move instruction here in FORTH, like I ran into issues with that because I wanted to vary like lots of data from one part of memory, from ROM memory, which is ROM in these like ROM chips, into memory that was internal on the die of the CPU, and this is hopelessly slow. So I quickly ran over like the budget, the frames per second budget. So I had to write it in assembly, but that's fine. That's kind of like fun to do. And what I did was like I chose like sort of like an adventure or like RPG setting, which means that it's not so resource intensive, or it doesn't need to be. And I had 3 months for it, which was not so much because I did not write my FORTH system at all, and I'd never really written FORTH in anger. Yeah, and so to put it all together, the way that the system works is you put your program basically on this thing, and in the beginning that was just the FORTH kernel. Then you use FORTH mode, written as I understand by Lars Brinkhoff, who is in the chat here, which asks you for a program and then just vary strings back and forth to that program. And so that's just that's a super easy interface. So I made that work with that shell that I had that interfaces with Game Boy Advance. And voila, as I somewhat showed, but not with FORTH, you've got a REPL, and you can just send code snippets from your REPL to your Game Boy Advance, which for FORTH people that's a standard normal thing to do. And as a Lisp person, I know a REPL, but like in an embedded system, that was new to me, and I thought it was just exciting that it worked. And I had already spent quite some time on getting this to work. But I tried to set up my system on this new OS and this new computer that I have, and I just ran out of time. So I'm just gonna show you what I had in my previous setup because I made a video on it. So if you can see this, this here is Emacs. And this is my file that I sent to the Game Boy Advance. Oh, maybe we should. So FORTH load file, and it just sends everything over. And't this sends everything to the screen, and at the same time compiles it as well on the Game Boy Advance. And thanks, Lars. If I'm guessing you were the one that did this, because it worked great. It was really nice. But you're just gonna run into trouble in some way, shape, or form. And the first one was there was no Game Boy Advance specific code whatsoever, and that is great because that is almost the funnest part of programming is you can do whatever you want. And so let's do it with okay. Oh, sorry, this one. And so that meant that like you need to put in all your constants. So there's like the Game Boy Advance has like a whole bunch of memory locations that you need to put in. There's a whole lot of video modes that you need to put in. So it has like a tiled mode, which means it uses tiles, or it has straight up bitmap mode. So addressing things one point at a time and moving stuff along in that way. Sorry. And then you need to think about how you ferry that around. And I had a great time trying to understand how to write in Forth and like going through like all of those like Forth sort of aha moments, make your function small because like maybe I can show that. Let me see. Oh yeah, I mean things like this, like alloc sprites, for example, and this thing. I think this is already maybe like becomes a bit too unwieldy to grok. So like I made like a little like allocator for like sprites that you like put on the that you put in memory, and you keep track of your sprites, so you can deallocate like sort of the concept of a sprite instead of the memory locations that contain the graphics for the sprite, that kind of thing. And oh my god, yeah, it was interesting in the beginning, but you live and you learn. And so I did get fairly far. Like you need to put collisions in. There are so many things that you need to think of with video game development. And to make it like nice, like the background needs to scroll, but then it hits some, you know, programming, you know how it is, I guess. Yeah, but the program, so in the end, I got to, so about 1,600 lines of Forth code with a lot of content in. And that is great, but like trying to load that on your Forth system, oops. Is a chore. It took very quickly, it took like half a minute to be able to load it on the Game Boy Advance, and that is unacceptable for video games. You can't ask somebody to sit around for like a minute to wait until your Forth system loads. So I figured you need to I need to compile it. I need to cross compile it. And that is nice. And ideally, I know you want to do that in Forth, and you want to do it the right way. But I had a deadline, and I did not have the time to do that. So I figured, like, well, how hard can it be? I'm just going to use Python. Don't crucify me. To do this because Forth is so regular. And that means that like basically all the immediate words, I guess, you need a special case and you need to put stuff in it, and it limits like you, but it's not so bad because of the way that the Forth was implemented. So basically every Forth word was also an assembly label. So that means that you can just output every assembly label as a memory location in assembly, and then you can just compile that with your assembly file that you have, if that makes sense. And that just works. And so that's actually quite easy. And so to have like a very simple, ugly it's not a cross compiler, is it? It's too simple and too hacky. But it took, I don't know, maybe 300 lines of code or something like that, and it worked. Like my idea is to at some point actually like implement like a proper cross compiler for it, and maybe I shouldn't do that myself, but it's kind of fun, I guess. And and that's it. And I had a system, and I was basically happy. And I can just show you what the end result was. So it is this thing here. You can jump to YouTube. Hopefully we don't get we do get an ad. Oh, let's skip back a little bit. So and the interesting thing about developing for these things is that you can't hear anything. Can you hear this? You need to implement graphics. You need to implement sound. So you need to make sounds. You need to make like the graphics, and that was all like really fun. It's a very multidisciplinary thing to do. So that's all just very fun, I think. And so what I had was this room. You can walk around. You can interact with certain things, and it will pop up dialogues. And yeah, so I was pretty stoked that all of that worked. Yeah, and that's it really. So all of this is up on GitHub. If you're interested to check it out, I called it Wrath, which is sort of like chariots in a way, because like it's like a chariot of like it's abstraction, whatever. I had something in my mind that sounded interesting, but yeah, look it up on GitHub. Also, the serial code is there, and all kinds of other code. Also, the old Common Lisp assembler is there if you're interested in that. Yeah, and I think that's it. That's that for me.
Okay, thank you very much. Thanks for the
Very nice,
presentation.
very nice. Nice.
Are there any questions?
Yeah, I would like to have a demonstration of the crux of the lecture. That is more demonstration of the game.
Right. Yeah. So there's the issue. Okay. So I had made like a whole system where so this is a GameCube, and this is actually a Game Boy Advance. So this is like an add-on that you can buy for GameCube, so you can play on your TV screen. And I bought like a connector from how do you call it? Like, so in the back here is actually like a digital out, which is fairly fancy, I think, for the time. You had to buy like a special GameCube to make that happen. And you can connect that to something that translates from this particular signal to an HDMI signal, because this doesn't know how to talk to HDMI. And I wanted to set all of that up, but unfortunately I just did not have the time to make everything work properly. So I can maybe do that like at a later time, but I just ran out of time to make like a proper demonstration of that. Yeah, I do have, if that counts, a YouTube video which you can watch that sort of demonstrates it, in which you can change certain things. Let me see.
And can you run this on a Game Boy? You don't need to make any hardware modifications to the Game Boy Advance?
No, nothing like that. So this just runs on stock hardware, because your communication is your serial port here. Okay. The only thing that you need is something. You need a way to put your information on the Game Boy Advance, and with UART. So there's a way to put a program onto a Game Boy Advance that can be the, so to speak, like the bootloader for a Game Boy Advance that can then start talking to your serial ports. But for that, UART isn't good enough. So you need one of the other communication protocols. And to work with one of the other communication protocols, like the timing is really strict for that. And And PCs have historically been quite bad at that. So what people have been doing is they've used an Arduino to get the timing right, and they then talk with the PC to the Arduino, and then from the Arduino to the Game Boy Advance. Then you can use one of the other protocols to actually load something on it. But the other way to go about it is to buy one of these flashcards, or you can buy a very cheap counterfeits. So unfortunately, there's lots of, I've never did that, but you can buy, and many people buy Game Boy Advance games that they don't know are counterfeit games, and they are programmed with a flashcard. So they're just rewritable ROM, and you can buy one of these devices that can put data on that. Or what you can also have is you can buy these cards, which have a micro USB card in it. So you can put whatever program you have on the micro USB card, and that will be seen as like the standard ROM card, because it has an FPGA on here that makes the illusion happen.
Thank you.
Great.
Well,
Additional question?
Christian would have a question.
Sure.
I was puzzled during the whole presentation about all the knowledge that you had to acquire to do this. At the very early stage, how did you get all the hardware information to be able to go so deeply into the Game Boy?
Back in the day, when I started this, so there's this thing called Tonk. Wait, what happens? Tonk DPA. So was this really nice Dutch guy. So this was when I was like starting off myself with programming. So I didn't know very much about programming at the time. That just introduces everything. So it tells you this is the Game Boy Advance hardware. This is how it works. And it was good for a newbie like me at the time, because it also sort of explained these low-level C things to somebody who didn't understand those things. And then, so that is basically enough. So it's fairly comprehensive. And then that's coupled with once you understand the basics, then you can use, this is basically a reference manual. So a person that wrote an emulator, this person also wrote sort of the, not really open source, but the open sort of reverse engineered spec for the Game Boy Advance.
Mm-hmm.
So in the summary, someone else had done all the reverse engineering first.
Luckily, yeah.
Okay,
Yeah, it's not totally trivial to, you need to like understand this on a deep level and poke around it. So what happens, like whenever there's like, whenever a new console would come out, there's like lots of these like teenagers with way too much time in their hands that are gonna, that form a community and try to one-up each other in showing that they figured stuff out. So it's this communal process. It's normally not one man is an island to understand this kind of stuff.
Mm-hmm.
Thanks.
Right. Other questions?
Yeah, I'm going to be selfish. I apologize, but since I've always had a question about exactly what does ARM sell? Do they sell, like, do I get like a file that I can send to a foundry that can actually implement an ARM processor on silicon? Is that basically what ARM, I know it's a license, but I've always, you know.
Yes, so there's two models. One thing that they sell is, yes, they sell the RTL files. So they implement their own cores. But then they also, so a lot of the phone makers, they will buy one, like the Cortex-M, for example. They don't just send that to the fab, but they will modify the design and like make it into like a proper SoC instead of just having like a CPU. And they might modify it if they have like the right license or whatever. And the other one is like ARM is also a platform, so it has an ABI and it has an instruction set, and that is sort of the interface. And so different manufacturers who make their own implementation, their hardware implementation, can talk to each other. And so that is something else. So some of them buy whole CPUs and others buy sort of the spec, so to speak, that they can use.
Because it can be rather complex, right? Because you can, like the way the hardware is implemented with pipelines and all those types of things. I mean, that's not a trivial thing to, and I guess, is that implementation specific, or is that part of the, or if you're going to implement it and ARM has developed it with a certain instruction pipeline, you follow that instruction pipeline?
Yeah, it's some things are and some things aren't, I guess. There's always this, there's a line which becomes in implementation defined, and that is where you get your speed or not. But they have a spec, and you're supposed to hold yourself to the spec, and then it's up to you how you want to implement that in hardware.
Okay, thank you very much. I appreciate it.
Yeah, one comment about the Game Boy. In 2000, year 2000, or around that time, it was a craze. Okay, the Japanese Nintendo just released it, and a lot of people get hold of it and develop lots of games on it. Because this Game Boy was really an open system, an open platform. Okay, that's a very nice ARM processor, ARM7 processor on it. But it also has a cartridge that you can put your program in it. So that becomes a very convenient platform to experiment with your programming skills. Okay, so you can, anything you can write into the cartridge, it gets executed on the Game Boy, and so. At the time, we put E-forth on it and made quite a few different programs out of it. It was a marvelous platform.
Yeah,
it's nice to hear people talk about it after 20 years.
Yeah. So you programmed for it as well?
Yeah.
Oh yeah,
Dr. Ting, one question: how are you doing? Are you recovering well in the hospital or at home?
Yeah, I'm still in the hospital. I was told I'll be discharged Tuesday, and I'm getting better, but the lymphoma is with me. It's a struggle.
Yeah. Okay. All the best to you.
Yeah.
Thank you.
All our love to you, Dr. Ting, and recover well.
Nice to talk to you.
Yes, Dr. Ting, get well soon.
Beg your pardon?
Yes, hope for a speedy recovery.
Okay, thank you.
Sure. All right. So are there any questions to Thies? No, not the case. So if we look at the schedule, then Brad had to leave already, and we will listen to his great talk on next month. So we
need to unshare the screen, Thies.
Yeah, please. Which means we're at the end of the formal meeting, and of course we can continue chatting. That would be possible. And Peter, yeah. So
this is the schedule, and I reserved the last part of the meeting for Brad, as you can see here, for having a nice question and answer for him, because there is so much expectation for this talk. And when we prepare the meetings, we begin from east to west, and we let Europe, of course, is in the middle of this trip. And in the last part, we have America, South America, and North America. And in the last also is included Canada, where Brad lives. But apparently Brad did not know about this, and he joined us in the beginning, and he was not with too much time today. So probably next month we can make this moving force and camera force presentation.
Yeah, I think so. We schedule him first, so then there will no be delay for him. So I think that would be fine.
Let me see. I have a short presentation, if you allow me.
Of course.
Yeah,
Okay.
you're welcome.
All right. Yeah, let me grab screen. Share. Let's see. Oh, boy. Okay.
That works.
My screen. From the beginning. Did you see my screen?
Right, we do.
Okay, good. All right. This is the first part of my presentation on the JavaForth machine. And the next part I would hope to present on the SV Fignition. So the summary is talk a little bit about the Java bytecode and the JavaForth machine. And I implemented in VHDL, Verilog, and System Verilog. So I have three implementation of the JFMs. And I also optimized the fourth auto interpreter for that, which I was very proud of. And I was able to prove that this JFM works without any I/O. Okay, let me just. I think the Java virtual machine bytecode specification is a very comprehensive document defining a Java real machine. Unfortunately, Sun was not able to realize it in Silicon. And they not that they are not trying, they have made micro Java and pico Java chip, but without much success. But if you look at the Java virtual machine specification, you can see a real forth machine hidden in it. And that's what I say Java forth machine. To review that a real forth machine can be implemented on the Java virtual machine bytecode. I used 65 Java virtual machine bytecode to build a 32-bit integer forth machine. I need 6 additional bytecode to complete the forth engine, especially the return stack. I think the Java virtual machine has deficiency in its return stack structure. Bytecode dealing with longs, floats, and doubles will be added when resources are not. So I have only a 32-bit integer forth machine. Of course, if we can implement all these various different data types, we'll get a real Java machine pretty soon. I need mega core libraries to implement multiply, divide, and barrel shift to satisfy Java bytecode. I divide, I shift left, I shift right, and U shift right. The tiny FPGA core in the ESP32 cannot take in this big library component. That's what Don Golden wanted us to use, which is ESP32 FPGA. It's just too small. So I first synthesized and simulated JavaForth machine on Quantus 2, still in VHDL. And the JavaForth machine was then ported to Verilog and system Verilog with very little effort. I think these three different languages are basically the same. It doesn't only syntactic differences. So you can convert one to other very easily. So I have three Java virtual engines: EJ32.VHD in VHDL, EJS32V in Verilog 2001, and EJSV32.V in System Verilog 2005. All three ran the same fourth auto interpreter that I wrote under F#. The fourth auto interpreter, EJ32K.MIF, was optimized for Java bytecode. So it is very tight. It is an ideal test bench for Java engine.
You finished it?
Yes. So, okay. So here is a picture.
What's the picture?
Yeah, I was giving a presentation.
Okay, sir.
Thank you.
Everything okay?
Yes, thank you.
Okay. Thank you, sir.
Sorry, the nurses came in and picked my lunch, picked my breakfast. So this is a picture of the JavaForth machine. So you have a memory, which is divided into variables, dictionary, free memory, input buffer, and output buffer. So on the left-hand side is the bytecode sequencer, which has the P register, program counting, and also the return stack, which will stack up the return the nested segment call. And from Chuck Moore's design, I also retained the A register. So with this mechanism, you can address data as well as program with the same setup. So all you have to do is set up the address O in to read either P or A, and it will put out the address to the memory. And then the memory, if you are reading, the memory goes into the data I register, and this data will be copied into the code register, and the code register will be decoded by the bytecode decoder, and which runs all the logic. And at bottom here is the data processor. So I have the T register and the data stack. So all the ALU operations take the T and S doing some ALU and then put the data back in the T register. The data stack and the return stack, they have to be pre-incrementing, post-decrementing. So the mechanism is use two registers, RP and RP1. RP1 always points to one above RP. So if you are doing the pre-incrementing, you use RP1 to adjust stack. If you are doing the post-decrementing, then you can use the RP. So this is the basic structure of the entire processor. It is very simple. Okay, so I think we have a pretty good implementation for the FPGA. So all the registers have this share the same mechanism, that it has a tri-state bus called register in, and this tri-state bus will take in a number of inputs, and the right input will be activated, and when the register load is high on the next rising clock edge, the register in will be latched into register. So this all the registers you are using the same mechanism to update their content on the rising edge of the next clock. I need to prove this JFM without any hardware, especially with the I/O. So I allocate an input buffer and an output buffer in memory. The outer interpreter gets sequential characters from the input buffer, and then the outer interpreter will put output characters into the output buffer. So you can execute the fourth outer interpreter without any hardware. Okay, and this way I have ran through many code through the outer interpreter and watch the correct characters appear in the outer in the output buffer, and thus prove that the outer interpreter was actually working. And I think the JFM was completely simulated in Q2 alone, without any hardware. Now, JavaForth machine is a 32-bit integer forth machine executing mostly Java bytecodes, and optimize the fourth outer interpreter served as a comprehensive test bench to validate JFM. So VHDL, Verilog, and the system Verilog were completely portable. Okay, here is the parse. Okay, that's all for this morning. Thank you very much. And I would stop sharing and entertain some questions if there's any. Thank you very much.
Thank you very much.
Dr. Ting.
Are there any questions?
Yes, Christian has one.
Go
Did
ahead.
I get this right? You're creating a Java virtual machine in the hardware, and this hardware will execute bytecodes for Java code, from which you're creating a forth. So
yes,
all this will run on the hardware.
The goal of the Quartus IDE is to help you design a chip or in software, in VHDL, Verilog, or system Verilog. So the end product, if I have a FPGA kit that can be connected into the Quartus 2 IDE. Then I can program the kit, the FPGA chip, and make it a FORTH chip. And on top of the hardware design or the circuitry, I also put in the software, put in the Atle interpreter. So the Atle interpreter, as in a FORTH dictionary, is part of the entire chip. And if you have the proper I/O device, you can move this design into a FPGA kit and actually see input, output, and FORTH working in that system. Now, you know, because I'm resource limited, I don't have any working FPGA kit anymore. So all I have to rely upon is the Quartus 2 IDE. And I wanted to prove the logically correct, the Atle interpreter correct, without any hardware. It's all in Quartus Simulator. Okay?
Okay. So more or less in the next presentation we get from you, if you find the right PGA, we're gonna have a Java virtual machine in hardware.
No. It's going to be very expensive.
Very expensive.
I cannot afford it.
Okay.
Yeah, I just had the first design to show that there is a FORTH engine that's in the Java virtual machine. Okay. If people realize that, you can build a FORTH engine and then embellish on it, build all the other things that Java virtual machine required, and build a real Java machine. But
Dr. Ting, money is no problem for Christian, so you can ask what you want, and he's
okay. Thank you.
Thanks.
Okay, so nice to see you guys. Yeah.
Thank you very much.
Okay.
And take care.
Next time.
See you, Dr. Ting.
Great. So 16:30 is the end supposed to be, which is
I think Rolf Hammerling has a question for the group.
yeah,
already.
sure.
About
Sure.
Exceptions or about floating point. Anything else is not allowed. Rolf.
Thank you for answering the questions in the group.
No, actually, the Java virtual machine specifies single 32-bit floating point and also double 64-bit floating point. So these are in the specification. If you really want to build a real Java machine, you have to do the floating point. There's no way around it, okay? But to do the floating point, you need the top-notch IDE and the biggest FPGA that you can get, okay? So that's out of my reach, okay? But I think I have the first step to show that we can launch that machine.
Thank you very much.
All right. So, Rolf, you had questions, or and you're preparing them, or?
I had questions, and they were fully answered in the FORTH group and the other group of Facebook. So there's nothing special I would need to know to continue. It is so I must concentrate on FORTH79 and FigForth, because to start with anti-forth is a boring idea. It's too big. So it will be very simple, everything. My father is so simple.
You have Brad Nelson here in the group to ask directly.
It's just a question, what's the difference between the assembly version and the C version? So I will do it in C, my force. But what was with your JavaForth difference from the assembly version to the C version? Where did you have to do things different?
But perhaps I misunderstood. So I with ESP32forth, it's a C-based forth as well. The other speaker I think was referring to a native forth, but yeah, no, the ESP32forth is a C-based forth because we want to use the libraries that are available on ESP32 and don't want to have to re-implement the Wi-Fi and Bluetooth functionality and so on.
The question is what must be different with this forth in C than everybody had done it in assembly language 10, 20 years ago, or now even there are some simple assembly language forth. So what is different in C?
I'd say it's a couple of things. One is just that using C has the benefit of being able to plug into these libraries, as I mentioned, and then I think most of the challenges in doing a C-based forth are coaxing the compiler into doing something that's not terribly inefficient underneath. For instance, in ESP32forth, we're using a feature called a computed goto to trick it to do something resembling what an indirect threaded forth would do underneath.
My problem was that I have to do so many checks which are inefficient to avoid that if I'm using interactive words that the system is crashing. And in the forum there was the comment, if you do a .s dot command on an empty stack and the system crashes, it's okay. No, it's not okay. So with every command I have to check, is there something on the stack, or is the stack full, which is less probable. And
memory protection is definitely an issue. Like unlike say JForth on a Linux, there's no trap handling, and then for the ESP32forth, the ESP32 doesn't have particularly good fault detection mechanisms. So one nice thing about Dr. Ting's design that I've been meaning to find some good pattern for is that because he uses a virtual memory space, none of the memory is dangerous to touch. But with ESP32forth, the current version uses raw access, which is dangerous. I probably need to put more safety in some of the default words. It's a good suggestion.
My problem is that I have to put repeated code within every word. So, and there is since 10 or 20 years, this extreme programming people from US, and they say, don't repeat yourself. But I cannot check anything with C, not with C++. With C++, I have the catch error, the catch trap thing. I have to check if every word in C or in Pascal the same within every word the same. There's something on the stack. If not, don't do it. Because I had also some problems. I had some macros, some defines, and it was not wrong. And so on C, even on Windows and Linux today, of course, everything crashes because it's not Python or Java. And this then makes the performance so bad. I'm not interested in performance, but if somebody says Forth is so fast and just calls to words by so Forth bomb is just the number of calls to functions. Then if in every function I have to check, hey, stack on this function must be 1 or must be 2, and if not, don't do it. Then this does not lead to an efficient system. So I asked, how was that 10 or 20 years ago with 2K of RAM, of ROM, or 8K of ROM and 2K of RAM to do all these checks. That all the Jupyter and the BBC Micro and the Hector computers, they didn't crash, I think. I have now the emulators, they don't crash. So if I say .s or s, there's no crash, of course not. But with C, I have to do this check in every single dumb function, and I cannot do it outside because I might write a word, especially later if I have my own words. Currently, I'm still interpreting that do an array, and they say I need 10 words on the stack, not 1 or 2.
Right. Can I have a little, just say something briefly about the fundamental differences? I think that I am sort of live. Am I live for this bit? It's not selecting me, but there you go. Yeah, the fundamental difference between C and Forth is that Forth is a virtual machine architecture, and so it specifies its behavior in some ways in a quite low level way, whereas C is just it's not a machine architecture, it's just like a virtual architecture. You know, it has an internal kind of like symbolic behavior, but it doesn't have an actual machine, a low level machine architecture itself. And that's part of the issue with converting between Forth and C, is that you're jamming against different philosophies in language all the time. So for example, when you call a function in C, you have to supply parameters, whereas and those you can't do push and pop with those parameters or swap or anything like that, as they're supplied on the stack in a C function. But in Forth, it's integral to how it works. So when you implement things like normal stack operations in Forth and you're trying to write it in C, then you've got to create your own data structure for the stacks and then have additional commands to be able to do that. And that's because you're jamming up against different philosophies and languages, ultimately. Is that okay?
Can I add to that? But yes, I agree. And the answer is to create your own stack in C and then to call functions having picked arguments off that stack.
So the problem is with any high-level language, I know Forth was originally written in assembly language, I have to do the checks or I bounce, I crash. And this, so I have, of course, to look at all the source code of other Forths, but most Forths, from what I heard, did not do checks within the word. So in the past, there were no memory managers. So 8080 or Z80 had no memory manager to prevent that if the stack is empty and the stack is decreased, and then there is memory access, that it does not crash.
Have you thought of using a circular stack?
You're muted.
Oh, I attempted to unmute. Can you hear me? No, I can't hear you. I I said, have you thought of using a circular stack? That is to say, the stack pointer is maybe an 8-bit value, and when it wraps around, when it hits the end, it just wraps around, so it can't do any harm. The answer will be wrong. It will pick up the wrong value from the stack, but it won't crash anything.
Yes. I was told, and I will do this as I have so many parameters, so many defines, I will do that with one parameter, but then the program does not crash in the memory, but it gets wrong false values. For example, if the stack is empty and I do a dot, then the answer must be the stack is empty. So I have to check, and not that.
Why would it have to say that it's empty? This is I think a different approach. If I do dot when I don't have anything on the stack, most forth systems will say stack empty, but give an error. There's even an error code for it. But I have no problem if it simply prints whatever it finds, wherever it thinks the top of the stack is, even if there isn't one. What's the harm in that? Because it's no worse than doing anything else that's wrong. See what I mean? I don't quite see why it's such an important issue for you.
Because with the next command, first I see it's a fault if a dot command is executed when the stack is empty. But if I don't catch this and just take the rotating stack, so then with the next command, so I have to do a break. So what can't be with the system? So break means you're not in the right state. You did a mistake.
Yes, but aren't you using an interpreter here? Don't you just type something? If you just type dot on its own, it says stack empty, or it prints something that you didn't expect because it's not on the stack. So put something on the stack, then type dot. Isn't that the feedback loop? Or is that? I don't quite understand why you say that there's a break. What are you breaking?
Break means that, for example, I have the option both to read from command line by a file or some text. So I start my forth with building the user interface. So I have options to read a file at startup, text file, or I can redirect the output, the input, so that the text file is transferred as if I would have typed. And if there is a condition with a false code during development, of course, at least, that there's some problems with the stack, then it must stop reading from the source. It must go back to the prompt or do something else.
Okay.
And now, so if a program is, this would be for development. It's like with debugging information, all the symbols with C, etc. If there is a production version, I might switch this off. But I also know that it is typical for engineering problems, IT problems, that something which you did not consider happens. Nobody expects with a C program that's there's a stack overflow. Nobody expects with a C program or with a Fortran or Java program that there is ever a stack overflow, because there's so much memory. And just with C software on an embedded system, when there is just 20 kilobytes of RAM or whatever on these microcontrollers, then this might happen. That's why you can set the stack. But the last time I said stack was with 8080 on Z80 on a CPN system, or they had a C compiler. But since MS-DOS and since 640K RAM, okay, I never had a stack problem. So, but
you can still have a stack.
The C stack problem. But with forth, I have this problem even on the lower end. The upper end, if I have enough space, it cannot happen. So if I have 1,000 bytes or 1,024 bytes stack, and I know there is not so much switch. It will never reach the upper end. So I might switch off the check for upper bound. But the lower bound had always been checked. At least if there's a fault, then I must say no. But the idea is that I have a production switch and a non-production switch. So all the checks switch off.
So there is some precedent. Like even Jupiter Aceforth actually had a mode where there was fast and slow, and it would actually switch out a piece of the inner interpreter to trade off speed versus doing a bounds check for the stack and other things on each run through. And I have toyed for ESP32forth adding something similar where because it's annoying now. Like desktop systems, like with GForth, they can install a trap handler, and so if you have an out of bounds access, it can it can fault, and then you get a catch and a throw, and that sort of thing would be possible, but would be certainly slower. But yeah, having a switch is certainly something that even back in the day with Jupiter Aceforth, they did things like this. So that's a possible direction.
The problem is that if I have a let's say desktop application or a kiosk application or POS application, which is not intended that somebody interacts with the system from the force prompt, then I can switch off after I tested the application, because I can be sure that there are no bugs, no software bugs, so there will be no stack overflow and underflow. But if there is the force prompt for an advanced user, then this user can, at this point, he gets a prompt, he enters dot, and tuck it catches. So I cannot switch off it, at least for interactive commands or commands, or have to decide that all interactive commands which are not entered by the command line are not checked, just those who are entered by the keyboard. This might be also a solution. Thanks for that. Do you know the command how to switch off this internal check for the Jupiter? Because from the things that I know that this was just to switch off synchronization of the screen. And I'm not sure if the Jupiter did something else. So
it's not very much checking. I believe it's maybe a stack underflow check, and it's fast versus slow mode. Yeah, and yes, it also changes the way that it does the screen, which is but it's both of those things, I believe, fast and slow.
Thank you very much. As we have the source listing for the Jupiter Ace is online, I will look for it. Thanks. So, but my system is not yet on this level, but for later a production system, I will definitely have a switch at compile time, so that if the application is tested, there are less checks. Means also that interactive, that I might even have two commands, one for interactive use, and the other one for if it's in a program, if it's called in a series of commands automatically. And how to check that, I don't know at this moment, but it's a good idea. So if it's in the compiled new word or in the primitive library and it's not by the keyboard, but then no switch. Thank you very much. This was a new idea.
Excellent. Anybody else has another question for the group?
Maybe I have one. I see that all kinds of languages create their own virtual machine. Forth, Java, LVM uses a kind of virtual machine as well. Python, Lua. why do they all create those VMs instead of going directly to the hardware?
I think
Who
it's
should answer? Howard, okay.
Okay.
Fantastic.
I think it's the principle of the operating system. As you know, Microsoft and Bill Gates came up with this brilliant idea called MS-DOS. So the idea is that you get everybody to buy your operating system, put on their hardware, and all the people that write programs write them to run on your operating system. It's very good. So the VM is a kind of abstraction of that, where you write your operating system not for particular hardware, but for a VM. So I think the reason is it's linked for, you're asking why do people use VMs, is because it allows you to define the interface between your hardware and your operating system or your application. Have I answered that? I'm not even sure I understood myself what I just said, but Forth doesn't have to have a VM. I don't know whether you're aware of that. That's one interesting point. Often it has, but I think VMs and operating systems are designed to lock people in so that everybody writes for your VM or your operating system.
So more or less, VMs are a way of being hardware independent?
Yeah, yeah.
Writing a code that is more general that could work with on more hardware.
Well, it's a bit higher than hardware, isn't it? It's